Okay, let's talk about alkynes. Alkynes are those structures that contain a carbon triple bond carbon. The ending is going to be in YNE. So, let me give you some common alkynes, and we'll give you both the UPAC name and the common name. So the common name for this structure is acetylene. And I think it's those acetylene torches that have a high temperature that we use for welding. Now, I have 2 carbons, so IUPAC, you'd say, is an ethyl group, so eth for 2 carbons, and then since I have a triple bond, this ethyne. Okay? This is called ethyl acetylene as my common name. But if you look at it, 1, 2, 3, 4. So, and my triple bonds at the 1 position. So it's 1, or it's bute, excuse me, 1 ine. Okay. Notice since my triple bond is at the end, this is a terminal alkyne. Okay. If you see something like this, the common name is dimethyl acetylene. But the IUPAC 1, 2, 3, 4 is going to be a bute 2 ine. So except for hearing acetylene, we don't often use the common names here. You go and revert to the IUPAC names. Okay? When you look at the degrees of unsaturation, you look at ethyne, it was C2H2. So 2 degrees of unsaturation. Can indicate an alkyne. Okay, so if you have 4 hydrogens that are missing, an alkyne is something that you can consider. Okay, the other thing you want to bear in mind is when we name it, alkenes have higher priority than alkynes, which have higher priority than alkanes, okay, and haloalkanes. Alright, so let's go through and give you some names. How you name it is going to be very similar to when we were doing alkenes and alkanes. Oops. Okay. So when you look for your longest contiguous carbon chain, okay, alkenes take precedence, so you want your alkenes in there, but if you can get your alkynes in there, that would be good too. So this is pretty straightforward here. I have an ene, okay. This is a 1, 2, 3, 4, 5. So it'd be a pent, 1 ene, 3 ine. And at the 2 position, I have a methyl. Okay, so that's basically how we go ahead and treat our alkynes. Let me give you one that doesn't have your alkene in it. Let's do Okay. This is a good start. So we want the longest, we only have alkynes and alkyl groups and halogens. So you want the longest carbon chain that contains my triple bonds. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have two choices then. We can go this way or we can go this way. So remember, when we choose it, if I go this way, I only have 2 substituents. If I go this way, I have 1, 2, 3 substituents. So when you have redundancy and you have to figure out, or you have to make a choice of which path, then you're going to choose the path, okay, that's going to give you the most substituents. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I have a diene because I have 2 of them. One is at the 1 position, the other is at the 4 position. Okay, so I have 8 carbons, so I have an octa. 1,4-diene. Okay, this is an isopropyl group. This is a methyl, and this is a bromo. So when we name it, I'll put it down below. Do the bromo first. 7, bromo. Then I comes before M. 6, isopropyl. Okay. 7, methyl. Octa. 1, 4, I ran a space here. Diene. Okay, so that's how you would name it. If I gave you a name like this one, 2 methyl pent 1 ene 3 ine. How would you draw the structure? So you have to follow this. You say, wait a second, how many carbons am I looking at? And we're looking at 5 carbons. So 1, 2, 3, 4, 5. Of those 5 carbons, that's my longest contiguous chain. At the 1 position, I have a double bond. And at the 3 position, I have a triple bond. Okay, sorry. And at the 2 position, 1, 2, I have a methyl. So now all I have to do is fill out 1, 2, 3, 4. The rest of my valences, 4, 4. In order to complete my structure. So this is 2 methyl, 1 or pent, 1 ene, 3 ine. Okay. Now what about cycloalkynes? Okay, because this is an sp hybridized carbon, an sp hybridized carbon, this is linear. So you're going to have a linear chain of like 4 carbons. Because of that, cycloalkynes are difficult to produce unless they're extremely large. So how large? We're probably talking about greater than or equal to 10 carbons before you can actually close the ring on itself. Okay, so we do have size limitations, so we really don't talk about the cycloalkynes too much just because of that. And this alkyne is an internal alkyne, as you can see inside the molecule. Okay, so let's just do one example before we move on the properties of alkynes. So let's name this one. Okay, it's a nice linear alkyne. Okay, and we know that we're going to end in -ine, so let's take a look at my longest carbon chain. 1, 2, 3, 4, 5, 6. So hex, and then we say 1, 2. We want that to be the smallest number. 2, -ine. Okay, and then 1, 2, 3, 4, 5. So it's a 5 bromo hex 2 -ine. And remember, this is an internal alkyne, so you won't see this stretching on IR. You'll definitely see the CBR stretching. Okay, so when we look at the electronic structure of an alkyne, we're just going to take ethine, or it's also known as acetylene. So basically, this is an sp-sp sigma bond. This is an spH or SPS. This is getting blurry. Let me just see. I'll make it a little bigger. That's an sp bond. sp bond. sp bond. sp bond. And there are my hydrogens. sp-sp sigma, sps sigma. Okay, but what about my pi bonds? So you're going to have a pi bond in the plane of the board, and coming out of the plane of the board will be your other pi bond. Okay, because remember, all your p orbitals are 90 degrees from each other. Okay, so sometimes you'll see us draw this. Well, here's my carbon, and we just basically draw almost like a cylinder of electron density. Okay, and this electron density, the cylinder, I have 4 electrons. It's for my 4 electrons in the 2 pi bonds. Okay, so sometimes you'll see us draw it that way. The reason we draw it this way, let me show you the hydrogens. So here are my hydrogens just peeking out. Okay, it turns out that with my electron density in this way, when we talked about NMR, because of the movement of my electron density, it shields. Okay, the magnetic field that's produced shields these hydrogens. And that's why in NMR this occurs around 2.5 ppm. Okay, so it's being shielded by my electron density. Okay, since they're sp orbitals, it's a much shorter bond because it's got 50% character of an s orbital. So if you look at your bond lengths, the longest one at 1.54 angstroms is my carbon bond, about 1.2 or 1.33, excuse me. It's the 1.2. This is about 1.33 because this is sp2, so it has more S character to it. And if you look at my triple bond, this is about 1.2 angstroms. Okay? What does that also mean in terms of acidity? Okay, if we look at acidity of my terminal alkyne, obviously an internal alkyne has no hydrogens on it, so it won't be acidic. If we look at something like okay, that's going to be my conjugate base of, give myself enough space here. Ethane. Okay, the pKa is about 50. No big surprise. If I look at ethylene, okay, that's my conjugate base, okay, and this one is about 44, okay. If I look at ammonia, this is about 35. That's a negative charge. And if I look at the terminal alkyne, this is about 25. Okay? And if you want to compare that just to an alcohol, you can see this. That's about 16 to 18. Okay? So it turns out my terminal alkyne here is going to be more acidic than ammonia. Okay? Now we use that when we do reactions. Okay? So erase it. Let's start. Okay, so if I take a terminal alkyne and I react it with sodium amine, this is a stronger base than the conjugate base here. So what I end up with is I end up with an acetylide ion, okay, plus ammonia, okay. So this is called butanine, yeah, butine, so butanide, so sodium butanide, okay. So what we're forming is alkyne is alkynide ion. Okay? Alright. This is an excellent nucleophile. Okay? It works particularly well on, so we'll do it for SN2. In particular, you want primary halides. Okay, and it's an extremely strong base. Okay, why primary halides and not secondary? For primary, it's less bulky because these tend to be pretty large nucleophiles. Excellent nucleophiles, but large. So if you're not primary or methyl halide, then you have to worry about elimination. Okay, so let's take a look at how we make this one and do a couple of reactions. So how do you make the sodium amine? So what you do is you take sodium metal and ammonia. Okay, so this is liquid ammonia. So we're talking about around negative 33 degrees Celsius. And what we do add is you add an iron 3 catalyst. There's a reason for this, because we'll see this type of combination again without the catalyst, and you get a different product. When you add the iron 3 catalyst, you get sodium amine, okay, or sodamide, okay, and hydrogen gas. The hydrogen gas will bubble out of solution, and that's what drives my reaction forward. Okay? So that's how we make it. So you should know how we make it. Suppose now I say, well, I have this is propanide, right? I mean propine. So suppose I take propine, and the first thing I do is react it with sodium amine. And the second thing I do is I react it with, let's say, ethyl bromide. Then the first part, let me just put that down in blue so you can see what's happening, is in step 1, that's a strong base, what you form. Okay, is my propanide, I have the sodium ion, and I have ammonia. Okay, that's from step 1. Put my sodium back in. Okay, from step 2, okay, now I have an excellent nucleophile, and I have a primary halide with a good group. My halide is a good leaving group. So my nucleophile comes in, SN2, backside attack, and my leaving group leaves. Now, why do I not draw it out specifically? Because you know it's a backside attack. This is an SN2. The only reason is because there's no chiral center. So you know it's inversion, but it's not going to show in your final product. So you would get CH3, C triple bond carbon, CH2, CH3. And you're going to get sodium bromide and ammonia as your side products. But the key is your organic product right there. Okay, so you've just done an SN2. Now that you know how to make your nucleophile. So, what can we do besides this? What kind of reactions can triple bonds alkynes do? Okay, so before we do that, the way the process works is we're going to learn how to make them, and then we'll learn how to break them. So basically, when we're doing synthesis of alkynes, the first one that you just learned how to do was an SN2. You take and acetylide reacted with the primary halide, and now you get a new alkyne, and it's an internal alkyne. Okay, so that's one way to do it. And this goes via SN2. And we mentioned this has to be a primary halide. Okay, so how else can we make it? Just so you know, if you have not a primary halide but a larger halide, then you would be doing an E2. So if your halide is secondary or tertiary, you would reform your terminal alkyne plus you'll get an alkene. Okay, and you'll be proceeding through E2. All right. So not that much fun because you're just regenerating what you started with. Okay. Just so you know, what happens if I don't have it? But let's talk about how to make it another one. Okay. So synthesis of alkynes through elimination. Okay. So elimination. What we do is instead of for alkenes, we only did the elimination once. We do it twice to make the alkyne. So you can start off with what we call a vicinal dihalide. Okay, and you can add your base. You can add it twice. 2 equivalents. The first one, you get your alkene. The second one, you get your alkyne. Okay, so what are the bases that we use? Okay, we can use something like KOH is very, very weak. We could use the, you can use amide, sodium amide. Okay, you can use KOH. Okay, all of these are high temperature. So we're talking about 150 degrees to 200 degrees Celsius. Okay, so far so good? Okay, so one way is by elimination, right? And let's take a look at another way is by, you already have the terminal alkyne and you're extending it, and so you're going to do that via SN2. Okay. Let's take a look at another elimination. So the other elimination looks like this. We had a vicinal dihalide. Now we can look at a geminal dihalide. And we do elimination. Again, you're going to add your base at a high temperature. And you're going to add 2 equivalents. And then you're going to get your alkyne. Okay. So let me just show you what happens. So here, I'll use a different color. When I add my first equivalence of base, okay, my base comes in, grabs the proton, and then that forms my double bond, and then I have my leaving group. So you form your alkene. And this is actually very fast. Now, when I add my second equivalent of base, again it comes in, grabs the proton, this comes in, and now this leaves. And I'll, so you can just see. And that's essentially how we get our alkyne. Okay? So it's basically 2 eliminations. What's interesting is this. How do you get a terminal alkyne? So here we're looking at it, and there are several ways you can get a terminal alkyne. You can do the same thing, but instead of having an R group here, you can have hydrogens there. Let's do the vicinal dihalide. Okay. You just add your 2 equivalents of base. But there's also an isomerization that can take place. So how do I isolate this? Because we know that internal alkynes are more stable than terminal alkynes. So, depending upon the base that you use, you can choose or select one type of alkyne over another. So here's the thing. When we are making a terminal alkyne, the preference is to use sodium iodide at high temperatures. Why is that? Once you do your elimination, you form, like we mentioned up here, your terminal alkyne. But remember, this is a strong base compared to my terminal alkyne. So it reacts with a third equivalent of sodium iodide, and you form your salt. Okay? And once you form your salt, it can't go back. So once you form your salt, this can precipitate out in your solution. So the way you select for terminal alkynes is use sodium iodide for terminal alkynes. Okay. For internal alkynes, if you're starting off with your dihalide and it's internal, then either KOH fuse or, okay, sodium iodide would work. But why do you prefer to fuse? Okay. It turns out that we can have, at high temperatures, we can isomerize. And if it isomerizes and you get a terminal out of it, then it's going to precipitate out. So this is preferred. Fused KOH is preferred to get your internal alkynes. Okay? Alright, so those are the ways that we make alkynes, just through elimination. What other ways can we make alkynes? Well, we can make what we call inols. Okay, so what are inols? Okay, these are alkyne with an alcohol. Okay, so how do you make those? Well, let's go back and let's talk about the fact that an alkyne alkanoide is a very strong nucleophile. So we had been always working previously with just alkyl halides. Let's try a different group. Let's do a carbonyl group. And why don't I give you just an R group here and an R group there. I'm going to put R prime here. So all these groups can be different. They can all be carbon hydrogens, but they don't have to be the same. But this is what's going to happen. We know the carbon on a carbonyl is slightly positive and the oxygen is slightly negative. Now this is such a strong nucleophile and a full negative charge that it will be attracted to this carbon. And these electrons get kicked out. So what we form is a carbon-carbon bond here, and the oxygen, the electrons went on the oxygen there, so that's a minus. I have an R and an R. And all I do is add just a little bit of acid to protonate that. And so now what we get is an inol. Okay? So, let's talk about how we actually, let's do an example. Okay, so I take something like propine. First thing I do is react it with sodium amide. Okay. Second thing I do is I'm going to react it with acetaldehyde. And the third thing I'm going to do is I'm going to protonate it. Okay, so what is my product? If you take a look, the first thing that happens, step one, is I'm reacting it really with my amide. Sodium is just my counter ion. So I'm going to form my propionide ion, and ammonia. Okay. Now with my propionide ion, I move on to step two. And what I get is this is a good nucleophile. So it's going to attack the carbon on my carbonyl. So now I have extended my alkyne, in this case by 2 carbons. In step 3, I now take my product and I protonate it. final product, my ionol. Okay, now do you have to show all these 3 steps, the mechanism, in order for you to write down your product? No, but what I like to do is show you what each of the steps are. So you can read this and say, oh, that's what's going to happen. So then I would get CH3, C triple bond C, okay, C OH, H, CH3, okay, and you would be able to just write down your product, okay. And do I want you to write down ammonia and the water? You don't, and the sodium ion, you don't have to, okay, because my counter ions would be that. The key is making sure you write down your organic products. Now, in this one, this is a chiral center, but none of this is chiral, so you're going to have a racemic mixture. So make sure you recognize your product and know that you're going to get a racemic mixture in this case. Okay, let's just take a pause here, and then let's start working on more reactions with triple bonds. Let's summarize the synthesis of alkynes before we move on to reactions of alkynes. So for the synthesis of alkynes, the first one we can do in SN2, where you have a terminal alkyne reacted with sodium amide, then for your second step react it with an alkyl halide, methyl or a primary halide, and then you get your internal alkyne. Second, we can make alkynes by doing an elimination. Okay, so you either have a vicinal dihalide or a geminal dihalide. Minimum 2 equivalents of base. Usually we just do an excess of base and heat. Okay, and then you form your alkyne. If you want a terminal alkyne, then you're going to use excess sodium amide. Then step 2, you're going to protonate with acid. Okay. If you want your alkyne to be an internal alkyne, then you would use preferably potassium hydroxide fused with, which means just pure melted potassium hydroxide. And that occurs around 200 degrees Celsius. Another way to make alkynes is when we make ionols, okay, and that is 3. You're going to take the terminal alkyne. Step 1, you react with sodium amide. Step 2, you're going to react with a carbonyl compound. It can be an aldehyde, it can be a ketone, it can even be an ester. We'll talk about that in a moment. Okay. And the third one, we're going to protonate. Okay. And what you get an ine, all with alcohol. Okay, so those are the ways we make alkynes. Now let's start talking about reactions of alkynes. So the first type of reactions we're going to talk about are addition reactions. And you'll find that they seem very analogous to the addition reactions that we did for alkenes. So let's take a look at the first one. If I take an alkyne, okay, and I react it with a compound AB, then what you get is you add AB across my triple bond. Now I take this and I add another AB, and so you get two additions across my alkyne. Okay, so let's talk about first things first. Let's do this with hydrogenation. Okay. When we do hydrogenation, what we do is we take our alkyne, we add a minimum 2 equivalents of hydrogen, and then we have a catalyst. We have a catalyst, typically palladium, platinum, or nickel. Okay? And what we get is we get the alkane. Okay. So that's what you get. Okay. Now the question is, what happens if you want to stop at alkene? So if you want to take an alkyne to go all the way to an alkane, you just add in your catalyst and your hydrogen, and you will get your alkane. So now we're going to talk about what happens if you want to stop at the alkene.